the moving force of the universe, massive mass ejection theory, and its difference from the nebular model. Welcome to this episode. Today we are asking a very simple question with a very large consequence. Where did the motion of the universe come from? Planets orbit stars. Stars orbit within galaxies. Galaxies themselves move. Rotation appears everywhere, from small bodies to enormous cosmic structures. Modern astronomy explains the formation of planetary systems mainly through models involving collapsing clouds, rotating protoplanetary disks, accretion, collisions, and gravity. NASA describes young planetary systems as developing from disks of gas and dust, where particles collide, stick, grow into planetesimals, and eventually form planets. But there is another question we can ask. Before a planet had an orbit, where did its particular motion come from? This is the question at the heart of the massive mass ejection theory, or MME theory, proposed in my book. Let us be clear at the beginning. MME is a proposed alternative framework, not an established replacement for modern planetary formation science. Observations of protoplanetary disks and planet formation strongly support disk-based formation processes. The purpose of this episode is therefore not to declare one model proven and the other disproven. It is to examine a different causal question. The question is motion inherited, or is motion initiated? Part 1. The standard nebular picture. The traditional nebular idea begins with a large cloud of gas and dust. As the cloud collapses under gravity, it develops a rotating disk. Material near the center forms the young star, while material in the disk gradually becomes planets and other bodies. Modern versions of this picture are much more sophisticated than the old textbook image of a simple rotating cloud. They include accretion, collisions, gas dynamics, magnetic fields, jets, migration, and the redistribution of angular momentum. In fact, observations of young stars show disks around them, and telescopes have observed structures associated with planets forming in these disks. So the nebular model has substantial observational support. But the MME question is different. It asks us to separate two things that are often discussed together. The existence of angular momentum, and the physical event that gave a particular body its momentum. Angular momentum describes rotational motion. It is a conserved quantity under appropriate conditions. But describing a quantity is not necessarily the same as identifying its ultimate physical cause. The MME proposal therefore asks, could an impulse have initiated the motion before the body became an independent astronomical object? Part 2. The forgotten impulse. Imagine throwing a stone. The stone does not begin moving because gravity pushes it sideways. Your hand provides an impulse. The stone leaves your hand with momentum. Gravity then changes the direction of its motion, producing the familiar curved trajectory. Galileo's studies of projectile motion gave us a powerful way of thinking about this. MME extends this intuition to the cosmos. According to the proposed framework, pressure impulse is the initiating event. A body is ejected from a parent system. The ejection gives it velocity and momentum. Once released, gravity can alter its trajectory. In this picture, orbital motion can be understood as an initially directed motion subsequently curved by gravity. The important distinction is this. Pressure impulse initiates the motion. Momentum carries the motion. Gravity regulates and bends the motion. This is the conceptual backbone of MME theory. Part 3. What is a pressure impulse? The theory proposes that when internal pressure within a massive body exceeds the conditions that contain it, matter can be expelled. The ejection may be associated with extremely energetic stellar events, plasma eruptions, explosions, or other large-scale processes. The proposal then asks whether some astronomical bodies could be the products of such events. The outcome would depend on the magnitude and direction of the impulse. If the impulse is sufficiently large, material may escape. If it is insufficient, material may return. And if the initial conditions produce a bound trajectory, the material may remain gravitationally associated with the parent body. In MME language, this gives three broad possibilities: escape, fallback, or bound motion. But an important scientific caution is necessary here. These possibilities do not by themselves demonstrate that planets were actually ejected in this manner. To establish that, MME would need quantitative models and observations that distinguish its predictions from those of existing formation models. That is, where a hypothesis becomes testable science. Part 4. MME and planetary formation. The strongest version of the MME proposal imagines the solar system as the aftermath of massive ejection events. The young sun, or an earlier parent system, would eject large amounts of matter. Different fragments would acquire different directions, speeds, and rotational states. Their later histories would depend on gravity, collisions, resistance, and interactions with other bodies. This picture offers an intuitive explanation for diversity. Why do different bodies have different rotations? Why do some objects have unusual axial tilts? Why are there retrograde rotations? Why are there objects on highly inclined or eccentric paths? MME interprets such diversity as evidence that individual bodies may have received different impulses. But here again we should be careful. Anomaly does not automatically prove ejection. For example, the unusual rotation of Venus and the extreme axial tilt of Uranus have several possible explanations within conventional planetary science, including collisions and long-term dynamical evolution. Therefore, these observations are interesting questions for MME, but they are not, by themselves, proof of MME. Part 5. Angular momentum. Cause or consequence. This may be the most philosophical part of the argument. The conventional framework treats angular momentum as a fundamental dynamical quantity. It is inherited from the initial conditions of the system and redistributed during its evolution. MME asks us to look one step earlier. If an object has angular momentum, what physical event gave that object its motion? The proposed answer is tangential impulse. A pressure impulse directed through the center would primarily produce translational motion. An off-center or tangential component would also produce rotation. In this interpretation, spin is not the original cause. Spin is the consequence of an earlier impulse. This distinction between cause and consequence is one of the central ideas of MME. Part 6. The hierarchy of ejection. The theory then proposes a hierarchy. At one level, massive cores may eject matter that eventually becomes independent gravitational systems. At another level, stars may emerge as secondary bodies. At another, planetary systems may develop. And at still smaller scales, asteroids, comets, dust, and plasma may represent residual or redistributed material. The attractive feature of this picture is its continuity. One generation of matter produces another. Gravity determines what remains bound. Pressure-driven events provide the proposed source of directed motion. But again, this hierarchy is a theoretical proposal. The actual formation histories of galaxies, stars, and planets are complex and cannot currently be reduced to one mechanism. Part 7. The two models side by side. Let us now compare the ideas directly. In the standard nebular framework, planetary systems form from material in a rotating protoplanetary disk. Gravity contributes to collapse and accretion, while collisions, gas interactions, magnetic processes, and angular momentum transport shape the evolving disk. In MME, the emphasis is different. Motion begins with an impulse. The nebular model asks how material in a disk evolves into planets. MME asks whether the material itself may have been launched with momentum from an earlier massive event. The nebular model emphasizes accretion within a disk. MME emphasizes ejection from a parent body. The nebular model treats angular momentum as part of the initial and evolving state of the system. MME emphasizes the physical impulse that produced the momentum. The nebular model naturally explains the widespread existence of disks around young stars. MME would have to explain those observations as well, and show that its mechanism can reproduce the observed properties of those disks. This is an important point. A new theory cannot simply explain one interesting feature. It must explain the full body of evidence. Part 8. What would make MME scientifically stronger? This is where the proposal becomes most interesting. If MME is to develop beyond a conceptual alternative, it needs predictions. It needs equations. It needs estimates of the energy and momentum required to eject planetary masses. It needs to explain how ejected bodies acquire their observed orbital distributions. It needs to reproduce the architecture of our solar system. It needs to address the observed protoplanetary disks around young stars. It needs to explain chemical compositions and isotopic relationships. And, most importantly, it needs to make predictions that could distinguish it from conventional formation models. That is the real test. Not whether an idea sounds attractive. Not whether an established theory has unanswered questions. But whether a new explanation can make successful, testable predictions. Closing. So, what is the central idea of massive mass ejection theory? It is beautifully simple. Motion is not merely inherited. Motion must have a physical beginning. According to MME, massive pressure-driven ejection supplies that beginning. The ejection gives matter momentum. The direction of the impulse determines its initial path. Tangential components can produce rotation. Gravity subsequently shapes, bends, binds, or returns the moving matter. This gives us a different way to look at the universe. Not merely as a collection of bodies that happen to be moving, but as a history of matter receiving motion, and then carrying that motion forward. Whether MME ultimately survives quantitative testing is a question for evidence. But perhaps that is precisely the value of a scientific hypothesis. It gives us another question to ask. And sometimes, a new question is the beginning of a new understanding. Thank you for listening. This is Sayyad Masthan Vali, author of The Universe, and The Universe Univocally. If you found this question interesting, consider subscribing to the channel. More episodes will examine the foundations, variables, and structure of the universe through observation, reasoning, and first principles.